And now, please welcome Dr. Carl McCants.
Thank you. I appreciate the applause, even though I can't see half of you in the room. My name is Carl McCants, Special Assistant to the Director for ERI, the Electronics Resurgence Initiative. I recognize I'm standing between you and the networking reception. Can I get a hand clap for the networking reception? So, please understand that what you see on the top, I actually came in last night, put in a bunch of sensors so that if anybody tries to fall asleep or nod off or use their phone, I will know. We're DARPA, we do these things, just kidding. In light of the fact that I'm between you and the reception, my goal is to provide you with new and interesting facts to discuss at the reception so that those discussions are with me and not about me. My God, did that guy talk a long time. Are you kidding me? I was hungry, I was thirsty, I wanted to get a drink. So, during this session, I'm going to discuss what we at DARPA see as the fourth wave of microelectronics and what we are doing to help maintain U.S. technological leadership in this critical area. Now, I know you saw this slide earlier from Dr. Tompkins. You did? You didn't? How many remember seeing this slide earlier from Dr. Tompkins? Okay, I'm a pretty interactive guy, so most people know that my other profession is as a preacher, so I will look for a little bit of call and response from you, okay? No, that was horrible. A little bit of call and response from you, okay? All right, so if you have seen this slide before, can I get a hand clap that I saw this slide before? What we're going to talk about, though, is a little bit more depth into what we mean by the fourth wave and where we're going with things. So what this shows is a change in the number of components in an integrated circuit over time. So starting in the 1960s with the invention of the circuit, we can see logarithmic increases that characterized each wave. So the first wave, okay, the first wave was going from the initial invention. You think about Jack Kilby, you think about what happened when, hey, we can put things together on a silicon chip, okay? We went from small-scale integration, SSI, to, you guessed it, MSI, or you guys are great, all right? And from medium to what? Okay, folks, look, you want to get to the reception? A little more participation, okay? Okay, then we went from LSI to what? VLSI, that's right. Very large scale integration, okay? Increasing the number of components, but more importantly, it was the innovations, the inventions, the understanding of the physics regard to the manufacturing science that pushed things forward. So that's the first wave. Then the second wave, okay? We went from aluminum interconnections and metallization to copper. Why? We started putting more things on the chip. Heat. And heat does what to components? Degrades the lifetime. So copper, a little better conductor. We could shrink things even more. The third wave was a transition from planar to 3D, the FinFETs. Again, DARPA had a little bit to do with that. What you'll notice, though, is that near the end of each of these waves, things started to kind of plateau. So at the 2019 ERI Summit, we discussed this emerging fourth wave of microelectronics. And what do we mean by that? Basically, the era of manufacturing microelectronics was coming into, if you will, a new era where we were leaving behind just simple device scaling, okay, and trying to push into where we'd be able to get higher performance, dictated by innovations in the third dimension. What are we talking about? Integrating heterogeneous components. So as the previous two speakers have talked about, where you're stacking not one, not two, but three different layers, okay? We think that, again, as we move forward, it's going to require the ability to push into three-dimensional heterogeneous integration, and we will talk about that a little bit more as we go on. So, when we think about this, okay, let's go with the first part of this panel. Now, traditional board, PC board. How many of you guys were curious as kids? Okay, I mean, I took things apart when I was little. Anybody with me? You wanted to find out where things were. And also, thank you, you had trouble putting it all back together, much to your parents' chagrin, because you realized, oh, I thought I knew what I was doing, but I really didn't. But if you pulled apart a PC, if you pulled apart anything electronic, you would see a board where you had the different chips kind of mounted side by side. Okay, my big thing was, you know, turntables, record players, and stereo receivers. When my dad came back from Japan, I was like, oh yeah, let's take this apart too. And he kind of made sure I didn't take apart his brand new stereo receiver. But anyway, getting back to this. Okay, we then went from kind of things being separate to together on a 2.5D interposer. Now, some of you may ask where the half D comes from. We can talk about that at the reception, okay? That's one of the things that we can discuss. That will be a good discussion. But we had active chips side by side connected through a passive interposer layer. What we're focused on, the panel on the right, is 3D, where we are stacking things on top of each other. And what you will also see is the fact that we have changed the interconnection pitch, we have changed the density, okay? And this shift from traditional monolithic manufacturing to the 3D changed the form factor. So now you think about how thin your laptop computers are, how thin your mobile devices are, things that you're probably wearing, if you're wearing a Fitbit, if you have an Apple Watch, if anything IoT, that changed in that form factor enabled by moving from standard to 2.5D and now moving to 3D has allowed us to do the things that we need to do and that we find in most of our microelectronics. So DARPA's convinced, moving forward, that 3D manufacturing will further push the boundaries of performance along with size, weight, power, and cost. Now, who's doing this? Okay, here's an example of Intel's Ponte Vecchio GPU chip. And you can see the stats there, just a couple transistors here and there. You've got compute tiles, you know, Foveros interconnection technology, Rambo tiles, a base tile, memory, everything else. Different process nodes, but recognize and keep this in thought as we move forward that this is primarily silicon, okay? Not that there's anything wrong with silicon. I mean, I love silicon, and you guys probably too. But, okay, same thing. If anybody in here is a gamer, AMD's new Ryzen 7, they have a 3D gaming chip. Again, you see primarily silicon layers of memory, processor, the backplane, all of that. So the bottom line, though, is that 3D integration is key moving forward. This shows kind of, you know, what is happening within the world. And in particular, we want to point out these four things. You know, first of all, Japan, again, significant funds with 3D. Singapore, IME participating with AMD, okay? TSMC at their Japanese center formed an alliance with not one, not two, not three, but 20 Japanese companies to push R&D into 3D packaging. And then Taiwan on the island itself, again, more things with that. So again, this is all to point out the fact that 3D manufacturing, the ability to do these things, to package them together in this configuration is very important. So, given this international activity, you may be wondering, what is DARPA doing to continue its mission of creating and preventing technological surprise? Can I get you guys to repeat that? What is DARPA doing? Okay, you guys, look. Let's try that again. What is DARPA doing to continue its mission to create technological surprise? I am so glad you asked. So we're confident that the portfolio of current and new research thrust in ERI will provide the necessary combination of basic and applied research, coupled with manufacturing sciences innovations to deliver the next generation capabilities for national security and national infrastructure needs. So, as I continue this talk, I'll provide an overview of ERI, the Electronics Resurgence Initiative, including the history, the current status, because that provides the framework and the background for where we're moving for this next generation of microelectronics manufacturing. And again, we have the next wave of ERI that's called ERI 2.0. So can I hear a 2.0? 2.0. Okay, I like that. So, ERI had its genesis about 5 years ago. Oh, we can kind of slow back down. Yeah, excellent. Right there, thank you. 5 years ago with the recognition that continued U.S. leadership in microelectronics was being threatened, okay, in both the defense and the commercial industry. So in 2017, July 2017, excuse me, the President's Council of Advisors on Science and Technology, or PCAST, issued a report talking about how do you ensure long-term U.S. leadership in semiconductors. So a couple things that the report pointed out. Number one, United States semiconductor innovation, competitiveness, and integrity faced major challenges. Number two, a concerted push by China to reshape the market in its favor, using industrial policies backed by over $100 billion in government-directed funds. And I should point out that in 2017, the Chinese government invested over $150 billion over 10 years, followed up the next year with another $100 billion, over 10 years. So those two examples, just for general, over $250 billion directed towards this industry, okay? And one of the more important points from that report was that the United States will only succeed in mitigating these dangers if it innovates faster, okay? With that in mind, with discussions that we had with industry, with academia, with other government agencies, these four things emerged, okay? And this is what motivated ERI. First, the increased reliance on advanced electronics, okay? And recognizing the importance that these have for national security and economic competitiveness. So if you think about where microelectronics components are found, it's everywhere. They're in your cars. They're in your televisions. They're in your toasters. They're in your TVs. In some places, they're even in your toilets, but we won't go there in terms of doing, analysis. No, it's an actual reality of doing analysis for medical purposes. But they're also in aircraft, both commercial and military, and satellites, and more importantly, the command and control and compute systems that are needed for this, so that when you take off from Columbus and go back to DC, that the air traffic controllers can trust what it is that they're seeing on their screen. So basically, again, this is what we're doing. The second point is the exploding complexity of microsystems, things that can do more. You've heard previous speakers talk about the complexity of computation, the complexity that is involved with using field programmable gate arrays, with using CPUs and GPUs and TPUs, okay? Exploding over time. Third, and probably of importance to this crowd, is the offshore movement of advanced manufacturing capabilities, something that's been over 40 years in the making, but the recognition that, hey, those that can do the manufacturing, those that understand the intricacies and understand the feedback loops between design, architecture, fabrication, package assembly, and testing, those are the ones that have the advantage of optimizing speed, power, size. And then the fourth thing was a recognition and emergence of hardware security threats. And again, we've seen what's happened. We've heard of Spectre. We've heard of Meltdown. Okay, these are things that impact the confidentiality. These are things that impact the integrity, the reliability of the microelectronics that we use, both in consumer and defense applications. And if you think about it for a minute, it's one thing to get the blue screen of death when you're using your desktop computer. It's another thing to get that same kind of blue screen if you're taking an F-35 and you're going Mach 1 plus. Little different scenario, but consequences are significant. So, with all that in mind, ERI was started. So this shows a timeline of ERI, starting with that PCAST report. ERI being announced in FY18 and the first ERI summit held out in San Francisco later that year in 2018. Again, attracting a large number of folks, luminaries in the microelectronics community, from industry, from academia, from government, all recognizing that this is important, this is what we need to do to really, really push forward. So we had that first summit in 2018, we had our last summit virtually in October of last year, and again, just really, really pushing on what is it that we can do in recognition of kind of the dual-use nature of the things that exist between government and industry. So what we've done then with ERI, that here are the 6 focus areas that we have done to date. And I'll go through these in just a little bit of detail to kind of, again, set the background, set the framework for what we're doing moving forward. So first, overcoming security threats through the entire hardware lifecycle. We've talked about what can happen, and as one consulting firm told me years ago, Bad hardware trumps good software every single time. When you're dealing with a system of hardware, firmware, software, if your hardware sucks, guess what? You're in trouble. The second, optimizing design and test for complex circuits and prototypes. Again, the importance of your EDA, electronic design automation tools, is critical as we move forward. The third area, securing communications. And not just thinking about 5G, but looking towards 6G, and also how do you secure comms in different spaces, in particular battlefield scenarios. Lower left, realizing heterogeneous 3D electronics. One of my favorites, you'll hear about that a little bit more. But again, recognizing the limitations of the 2.5D configuration and the need to go to 3D stacking, again, as you heard the previous speakers talk about. The next one, AI. Hardware to make decisions at the edge faster. Again, the implication that we have so much sensor data coming in, how do we utilize AI to make decisions, to go from data to decisions much faster? And then the last one, increasing the information processing density and efficiency, also related, because again, as we can take in this information and take it from multiple sensors, that gives us the opportunity to, again, go from data to decision much more quickly. So this is what we're doing now. This is current ERI. So in looking back at where we were, where we are today, the factors that motivated ERI are even stronger than before. And I want to talk about a couple things that kind of illustrate that. And first, the enormous offshore investments in commercial electronics by near-peer allies and adversaries. It's grown, okay? And you see the consolidation of leading-edge silicon manufacturing and increasing footprint into state-of-the-art packaging by what were formerly pure-play foundries. The second thing are microelectronics supply chain concerns, okay? Spurred by the disruptions caused by COVID-19, recognizing the global nature of the supply network, and more importantly, as you see the trickle-down, the ripple effects that exist today. As a quick example, there are car companies that have unsold inventory. Why? Because they can't get a chip that controls something as simple as your heated car seats. And in these climates, you guys know how important heated car seats or the bun warmers are, right? Right. So the result is that ERI must continue to strategically invest and seed new approaches and technologies to maintain our position in electronic systems. So where are we now, and how are we doing? So basically, one of the more important things is that ERI has increased participation from non-traditional partners from commercial industry into DARPA programs. We've fostered collaborative projects involving 6 of the top 10 semiconductor sales leaders, okay? Collaborative projects with all of the top 5 defense contractors, and collaborative projects involving all the top 10 research universities per U.S. News and World Report. Now, I have to say, even though I am here, that includes, as Coach Hayes would say, that school up north. Okay. As well as you guys, okay? Thank you. Uh-oh, we have one UM graduate in the house. All right, all right. So what is really important, though, is that we've increased the number of folks that are participating in DARPA programs. And that's one of the reasons that we're here. We want to hear your ideas. We want you to become a part of who we are. We want you to become a part of this supply network of supplying ideas and innovative concepts to help us move forward. So to give you an idea of what's happened, some of our successes in ERI, okay, processor architectures, okay, that are 100 times faster than standard CPUs and GPUs. This is the Hive program. And again, I want you to see these and hear these and think about it in terms of this is where we're moving in terms of going forward, because again, DARPA, we're looking at 5, 6, 7, 10 years down the line, and these are the kinds of innovations that we will need to continue to do that. The next thing, development of programmable hardware architectures to increase processing efficiency, okay? Integration of machine learning into tools for EDA. Again, how do we more smartly design and deal with things, okay? We're looking at the ability to process information while it remains encrypted, okay, the DEPRIVE program. And one of the neat ones, again, given my background in photonics, integration of lasers on silicon wafers, LUMOS. So looking at what we've done, where we're going, what's happening with ERI. So ERI 2.0, can I hear a 2.0? Thank you. And next generation microelectronics manufacturing. Okay. So here's kind of where we are. Again, we announced the ERI 2.0 thrust last year. We've actually started ERI 2.0 already. But I'll start off with, with the benefit of hindsight, what have we learned? Okay, first, it is possible to engage the academic, the commercial, and the U.S. government microelectronics communities in relevant, cutting-edge, dual-use research projects. Let me say that again. Relevant, cutting-edge, dual-use research projects. Two, it's possible to provide leap-ahead capabilities in computational efficiency, heterogeneous integration, hardware security, electronics design, AI components, and secure communications through these collaborations that benefit both the government and the private sector. And then for both the government and the private sector, maintaining technical advantage will require continuous innovation. At our previous meeting in Pullman, one of the participants on a panel said, nothing is static. And as you heard Dr. Tompkins say earlier today, everything is moving. So we have to continue to run faster than our competition. We have to continue in doing that to provide settings, to provide the capabilities needed for you in academia, for you in the corporate sector to move faster. And we want to be there to help do the pushing or the pulling to do that. So in ERI 2.0, we've introduced two new thrust areas. First, manufacturing complex 3D microsystems. Let me say that again because, yes, I smile when I think about manufacturing complex 3D microsystems. In fact, I would like for you to smile whenever you hear manufacturing complex 3D microsystems. Why? Because as you heard some of the previous speakers talk about, this 3D manufacturing is one of the keys as we move forward, okay? And then the second new area is developing electronics for extreme environments. And I must channel my inner MTO deputy director by saying extreme environment electronics. That's what we're going to do. Okay. So earlier, you asked the question, what is DARPA doing to continue its mission of creating technological surprise in this area? So to do that, I thought I'd employ the help of my friend, Mr. Montoya, who said, you keep using that phrase, 3D heterogeneous integration. I do not think it means what you think it does. To which his friend Vicina would say, inconceivable. And then Fezzik would say, well, that doesn't seem very sporting to me. So, I want to say though, when we talk about 3D HI, okay, we're focused on not just silicon, but other materials. Again, as you heard some of the previous speakers talk about, photonics, RF, MEMS, okay, all of this stacked within a single package. So again, going back to that first new thrust, we believe that now is the time for the community to push on technologies to manufacture complex 3D microsystems and put them into disruptive systems. Excuse me. So, what are we thinking about? Multi-chip, multi-technology, assembly, and packaging. Tools for design, simulation, and test. Security, 3D HI interconnects, thermal management, and power delivery. So real quickly, multi-chip, multi-technology, assembly, and packaging. When you start talking about now integrating different types of materials into the same package, when you have to address now the differences in terms of the heat generation, how do you deal with the heat, how do you optimize the performance of each level, of each layer within that package? What's the best way to put that package together? Do you go with ball bonds? Do you go with mini ball bonds? Do you go with hybrid bonding? What happens if you want to increase the density of those bonds? So again, you can think about fundamental studies that address now, because as you get closer and closer, you have to start thinking more about the interfacial physics involved with what's going on. Tools for design, simulation, and test. In discussions with the major EDA vendors, it's become very clear that the ability to do that simulation, the ability to have the multi-physics models necessary to look at what's happening when I have gallium arsenide or gallium nitride or aluminum gallium arsenide or mercadtel or silicon, silicon germanium, all of these things within the same package. And to be able to reliably and repeatably model and understand, the closer I come to being able to do the verification and validation needed to verify the integrity, to verify the performance of what it is that I've now put together, and to say that, yes, this gives me a performance advantage compared to what I could do with 2D or 2.5D. The security, as I'm putting more of these things into a package, how do I verify that what I put in is what I thought I put in? How do I verify that as I assemble these things together in this new 3D configuration, that I haven't introduced some type of vulnerability? And that ties back into tests. As a matter of fact, NIST a couple months ago released a new report talking about semiconductor manufacturing. And they looked at the ability to do simulation of materials, simulation of the manufacturing process, the testing, all of what's necessary in order to do this. Because again, my background is with Hewlett-Packard, and guess what? If you can't test it, then you don't know what you've done, okay? The 3D-HI interconnect. So now we're talking about going vertically. How do we do that? How do we optimize the interfaces? How do we optimize the material properties for all the things that we need to do? And then last but not least is thermal management and power delivery. What's the optimum way of delivering power to each layer within this stack? How do I co-optimize electrical performance and the thermal management? So those, again, some of the research areas, and I will say if you are thinking about it, if you have some ideas, please, please come see me at the reception. Okay, in addition, we are also going to create a national capability for 3D-HI, a 3D-HI manufacturing center by establishing a public-private partnership, or PPP, for research services for prototyping and low-volume production. And what you see on the slide is what we envision that this will look like. You'll see that the users include industry, academia, and government, with a national facility where we will have stable manufacturing processes and a 3D-HI assembly design kit, the equivalent of the fabrication wafer fab PDK, or process design kit. The output, two really important things. One, 3D-HI hardware prototypes. And then second, a digital twin. So what we hope this will do is reduce the time for manufacturing for 3D-HI microsystems, assembly and packaging, ensure secure supply chain with domestic facility, and again, the thinking is that the capabilities developed here will enable us to do things we couldn't do before, provide technology for advanced packaging and assembly with the potential for significant cost reduction in microsystems. So as part of the manufacturing thrust, we will continue to have the dialogue we've been having with the goal of getting these things prototyped into the hands of transition partners and users. And again, we will continue to push on all the things, all the different thrust areas into this. I can tell you that with regard to this particular effort, we are currently in the process of receiving proposals with phase 0 of this effort that is called NGMM, or Next Generation Microelectronics Manufacturing. I know a very inventive name, but I needed to come up with something, and I did. If you have ideas for me, you can tell me at the break. Thank you, thank you. So, the second new thrust area is extreme environment electronics, and when we get to the reception, I'll do my WWE impression of extreme environment. But basically, number of applications for these, for the DoD and commercial industry, and MTO recognizes that now is the time to take them on. So when we talk about the word environment, what does it mean? And no, there's not another Inigo Montoya to say, you keep using the word environment. I don't think it means what you think it does. When we talk about that, we're looking at Military Standard 883, which defines environment as the natural elements and conditions surrounding military and space operations that could have deleterious effects on electronic systems. So basically, if I take this and stick it in a jet engine, or if I take this and actually take, if you have an older system, you take the, the heat gun for hair, what happens to, the components on my PC board? What we're talking about really, though, are systems that not only tolerate, but thrive in these extreme environments. different way of thinking, because now you're looking at a combination of the electronic materials themselves. You heard earlier about the improved thermal performance of wide bandgap and ultra wide bandgap materials. You also have to look at now the package. How do you package things to thrive in these extreme environments? And so when we talk about here in the Department of Defense, electronics for extreme environments, we tend to focus on 3 elements and conditions in particular. And so the first has to do with high radiation. Next is extreme temperatures. And then high power, which is high voltage or high current. Each of these elements and conditions present their own unique challenges and opportunities. We will pursue research in these areas in ERI 2.0, and once again, if you have some ideas, if you have expertise in radiation environments, let us know. If you have expertise in high power, let us know. If you're used to switching things, EGFETs at 5 kV, 10 kV, or higher, let us know. If you have, again, expertise, experience in other high temperature environments, let us know, because we are pursuing these areas. So, in conclusion, I'll leave you with the following thoughts. And again, this would have been me kind of pulling something off and saying, hey, what is that? That looks pretty good. Dad, I couldn't put it back together, sorry. Maintaining U.S. supremacy in these semiconductor technologies over the long term is going to demand continuous national investment in disruptive technologies. And again, at DARPA, we will continue to invest in these disruptive technologies, utilizing your ideas. Second, future microelectronics innovation will be tied to the ability to design, fabricate, test, and model the performance of these complex 3D assemblies. Again, composed of heterogeneous microelectronic technologies. And then finally, fully automated 3D HI packaging, assembly, and testing represents an opportunity to accelerate and reshore future manufacturing. If you think about the current automation that exists in the wafer fab process, and if you haven't been to one of the microelectronics manufacturers, I highly recommend that you do that to see the overhead system, what we call the automated material handling system, with these FOUPs of 25 wafers whizzing around going from station to station. Imagine if we could do something similar to that for packaging and assembly, to where you minimize the number of humans required to do that. The ability to do that would represent a significant leap ahead for this country. Thank you for your time and attention. I look forward to positive discussions with you during the networking session. Thank you.
Thank you, Dr. McCants. And if you have a few moments, we do have some questions from the audience.
I was trying to get the reception, okay? You guys know, I was like, after time, I'm like, yeah, I'm thirsty. Okay.
First question. What role will chiplets play in 3D IC heterogeneous designs?
Chiplets will play a role, and the first thing that comes to mind is which definition of chiplet you're talking about, but the real key here is that if you have something that is a complete little system on a chip, or a complete chip that can go into a larger package, that will be a part of it. If you think about some of the things that are already happening where we're using chiplets, and I think about getting away from just a standard definition where you've taken a large processor and broken out into its individual components, and you're kind of placing those in different lateral locations on a die. I think there are opportunities to take some new innovations with chiplets and stack them up into these new 3D HI configurations.
Okay, thank you. Another question that's come in, what new programs is DARPA considering that will overcome security threats across the entire hardware lifecycle?
We have some program managers, one of which who is here, who is specializing in looking at hardware threats, and I will recommend that you talk to him, Dr. Lakian, who is dealing with hardware security threats. Other parts of what we are looking at and have been looking at, yeah, there are a few new programs that are still in the works that I can't talk about right now.
Okay, thank you. Another question, how do you intend to ensure that 3D HI capabilities demonstrated under NGMM remain a differential advantage for the U.S. versus migrating to offshore competitors?
Great question. I think one of the key things has to do with the innovation ecosystem that we currently have here and the folks that we're working with. Something that is of prime importance to me, given my background and where I was before I came to DARPA, I think there are opportunities to do the demonstrations of the technology here. Ultimately, what we've seen is that things really come down to economics. And what's going to be important really has to deal with how do we ensure that this is seen as economically viable to our US-based companies, as well as basically monitoring what is happening, to be quite honest, with some of our adversaries who's trying to pull this. Again, a number of things that I think we do and that we can continue to do, but it really starts with presenting the technological and the economic case to our onshore manufacturers.
Thank you. We have another question. How do you envision that the 3D-HI Manufacturing Center will be able to handle all the possible combinations of semiconductor technologies that may be presented for an arbitrary 3D-HI system?
Another great question, and I will say that is precisely why what we're currently doing with NGMM is conducting a phase 0, where we are literally polling the community to help us define and bound this problem. We recognize that if we are too broad, that it will not provide much benefit to the community. If we're too narrow, it will not provide much benefit to the community. So what we're looking to do within the context of NGMM Phase 0 is to say, hey, present to us some exemplar microsystems, as well as the associated equipment, tooling, both hardware and software, that would be needed to do this, so that we can adequately bound the problem and recognize that there are certain things that we should be working on, there are certain things that would be nice to work on, but if we can focus on this subset of all the possibilities that are there with regard to 3D-HI microsystems, that this will provide the most benefit to the government and the commercial communities.
Another question from the audience. You mention, quote, ensuring a secure supply chain, unquote. But how will the 3D-HI Manufacturing Center be more secure than any other foundry/packaging facility, aside from being offshore?
Aside from being onshore. Another great question. So I think one of the issues there is that there's the opportunity to learn from what is currently happening at our existing domestic facilities, as well as understanding the processes needed to protect things. So, and I will also say when it comes to ensuring a secure supply chain, the aspect of the security within this part of the overarching supply network involved in microelectronics, what do we do to make sure that when you present your design and you give this to the center, that there is a high confidence that what you get is what you expect to get back, as well as we've taken adequate steps to ensure that nothing has been done to tamper with that, if you will.
Next question. Even if ERI 2.0 succeeds beyond its wildest dreams, how will we be able to catch up with China, which is investing over $100 billion in the semiconductor sector?
Another interesting question, which has an interesting implication, and that is that we are behind China when it comes to innovation. Are we investing as much as they do from a strictly monetary point of view? No. But if ERI succeeds beyond its wildest dreams, guess what? We will maintain and extend the leadership that we have. That will, we believe, will spur additional, shall I say, investments in this country to continue. Nothing helps success like success. So if we're able to do all the things that we want to do in the original 6 areas plus these two new areas, and recognizing the interdependency between the 8 areas, if those are wildly successful, guess what? That will become a self-feeding, and again, it will continue to push things moving forward. So, yeah, again, we'll be able to catch up with China in terms of over $100 billion in the semiconductor sector. That part I don't know, but what I do know is that we currently have a technological advantage over China, and if we continue to push forward with these technologies, and if they're all successful, we will maintain and extend that advantage.
Thank you. Another question. Can you describe some example electronic systems that will, quote unquote, thrive in extreme environments?
Another great question, asking me to predict the future. But, let's think about this. And so what we're really talking about is attempting to design things. When you think about hypersonics, can I maintain computation? Can I maintain navigation? Can I do some things that I can't do now at the temperatures that we know we'll experience with those? Can I create additional sensors and the monitoring systems that would be necessary for jet engines, that would be necessary for oil drilling, that would be necessary, heck, for some of you in your homes because you keep it really, really hot. But really more so, it has to do with creating things and leveraging our understanding of what's happened in the existing examples. Again, having had conversations with folks at GE and United Technologies in how they're doing that. The packaging comes with that. So it's, can I design computation, can I design logic, can I design sensors that can withstand and operate almost as normal in those environments? So those are the things that we are envisioning in terms of moving forward.
And our final question from the audience, what is DARPA's role in the CHIPS Act efforts?
What is DARPA's role in CHIPS Act efforts? So one of the good things about being at DARPA is that I'm at DARPA, yay. Our role has really been to talk with and work with other folks in an interagency manner. So the MTO director, Dr. Mark Rosker, is one of the co-chairs of a group that's been meeting for the last year and a half, talking about the things that can and would happen. We've been meeting talking about how we coordinate and deal with some of the R&D needs moving forward. But that's primarily it. It's been providing scientific and technical input to those that are in the positions of making the decisions about the CHIPS Act, in particular with those in the Department of Commerce and NSC, National Science.
Great. Well, thank you again, Dr. McCants,
Thank you.
And thank you all.